Bismillah ar-Rahman ar-Rahim, my dear students of Biopharmaceutics and Pharmacokinetics 2 course, third year students, Ajman University. I would like to welcome you to this new topic, and this topic is the intravenous infusion. Intravenous infusion. In comparison to IV bolus administration, or they may call it IV push or IV injection. Intravenous infusion is the administration of the drug over some time. This sometimes can be 15 minutes, 30 minutes, or even more. While IV push or IV bolus takes place in probably less than 1 minute. So here we are administering the drug slowly. Okay. The similarity with IV bolus topic is that we are injecting the drug directly into veins, so there is no absorption process. Instead of absorption, we have infusion process. We have infusion process, and the drug gets to the system over some time, not at zero time. All of the drug is inside the system. Actually, no, this takes some time, so the drug gets in at slower pace. Are we talking about one compartment model? Yes, this is one compartment model. Are we talking about first order kinetics? The elimination rate? Yes, it is first order kinetics, but not the infusion rate. Okay. Okay, what you are supposed to be able to do after finishing this topic, you are supposed to be able to draw the scheme representing IV infusion and one compartment model. You should be able to write the differential equation. Okay. Type. Another thing is you should be able to recognize the integrated equation. As I told you, you don't need to know how this differential equation was integrated, but you are supposed to recognize the integrated equation and use it correctly. You are supposed also to calculate KL, or rate of elimination constant, and V, and you already learned from part 3 of IV bolus administration. إنه KL multiplied V شو بعطينا? What does it give us? It gives us clearance, drug clearance. طيب, another thing is you are supposed, this is very important, design and calculate appropriate IV infusion. So for example, if I tell you I want to reach a concentration of, let's say, 15 milligram per liter, then you are supposed to tell me what infusion rate I should give, for how long, etc., etc. You will learn later that infusion alone, for infusion alone, the drug to reach the desired concentration, okay, can be very, very long. So instead, we can combine fast infusion followed by slow infusion, or give an IV bolus followed by IV infusion. So we have different scenarios in order to reach the desired concentration so quickly. Okay, now let's talk a little bit about IV infusion. Why we shouldn't give the drug as IV bolus, مثلا? We have some drugs that can result in transient toxicity, يعني temporary toxicity, if we give the IV injection all at once. So in the beginning, some tissues, some organs will be affected adversely by how much drug you have injected. So instead of giving the drug all at once, we give it over some time. Type. In comparison to oral, for example, some drugs are degraded after oral administration because of stomach enzymes and pH, or because of first pass metabolism, so a lot of the drug is removed before it reaches the systemic circulation. Additionally, it will take some time before the drug can give an effect. So IV infusion would be good choice. Those patients who are bedridden, يعني قاعدين في التخت نايمين, they are beds, sleeping or staying in the beds in the hospital, and some already are receiving intravenous fluids. Instead of injecting them or having a new injection of the drug, what we can do is we can use the same line of the intravenous fluid to administer the drug كبيجي-باك, بيحكوا له piggy-back, provided that the drug does not interact with the fluids that are administered to the patient. Okay? Now, it's also very important to take into account how fast is the infusion process. For some drugs like vancomycin, if you infuse the drug rapidly, you may have what we call red man syndrome. Okay? So what I mean to tell you is that intravenous infusion can be useful in some cases. Before we start and I show you everything, here we want to draw the diagram that represent one compartment model, first order elimination and infusion. And the infusion, we are going to represent it as K0. بدنا نحكي له infusion rate, we will call it K0. This is the infusion rate. And the units of the infusion rate will be, for example, amount per time. Amount administered per time. Like, for example, milligram per hour. Now, someone will ask me, will tell me, okay, we are infusing fluids. And fluids, we should be caring about concentration. Well, in pharmacokinetics, we care more about the amount that gets inside the body per time. We care more than concentration. Of course, concentration or speed of the fluid entering into veins is very important. They are very important things. But in kinetic, we want to look at the amount that enters per time. So we agreed that this is the infusion rate given the simple K0. Some books, they give it the simple R. So either R or K0. And 0 here has a significance because it means that the order, the kinetic or the order by which the drug enters is 0 order input. إذا الانput في البody نعتبره 0 order, not first order. Now, what does 0 means? 0 means that this rate is constant. And this is what happens in reality. When you want to give an infusion, يكون في عندكم patient and you want to give an infusion, شو بتسووا؟ بالpump, you adjust the speed so that certain volume enters per time, or the volume of fluid is administered in a given time. فإذا في عنا constant speed or constant rate at which the drug enters the body. So let's now talk about the process. We have one compartment. Here we have the concentration in the plasma, and here we have the window through which the drug gets out, and the size of this window, we will call it KEL. Okay? Now, this looks like before. Before شو حكينا? If you remember, how does the concentration changes here? If you remember, we used to say, okay, delta Cp divided by delta T is equal to minus KEL في CP. You remember this equation. Okay. Well, it holds true, still holds. Here I need to add something. If I multiply change in concentration by V, then I will have change in the amount. بصير عندي ايش؟ amount change per time. Okay? فإذا if I multiply this by V, I can multiply this by V. فشو بصير الإيكويشن؟ delta CP divided by delta T is equal to minus V KL. طبعا this is the clearance multiplied into CP. Okay? طيب. Now the thing is, yes, this is correct, but we have something input, and this input is the K0, okay, which is a zero order input that increases the concentration. طيب احنا عندنا negative output, so the drug goes outside from the compartment, but we have also something positive, rate of input. فبصير هلا if I want to describe this one اللي هو infusion adding more drug inside and elimination removing the drug, then now I can calculate or can write the differential equation. Let me just write it as differential equation. Okay, I will call it DCP بصير عندنا DCP divided by DT equal to positive input that is K0 وبرضه هذا amount per time. لاحظوا انه please note that I'm trying to make the unit similar. فإذا I will multiply this by V بتصير amount per time okay, equal to K0 positive, which is amount per time, minus, you need to remove the rate of elimination اللي هو V if KEL في CP. Okay, this is your differential equation that you should be able to write based on this scheme here. Okay, based on this scheme, your differential equation will be V if DCP divided by dt equal to K0 minus V if KL CP. Okay, before we go further, you will notice that at the beginning شو بيكون الكونسنتريشن at time 0. يعني لسه يا دوب just the drug wants to enter. At that moment the concentration is 0. فإذا what you will have is positive. So the change in drug concentration في central compartment أو let's say one compartment, this change will be positive. ليش؟ لأنه K is more, or the rate of input, I بدي input is more than the rate of output اللي هو negative. إذا input more than output. فشو بصير عنا؟ بصير عنا change here. The change here is positive. حلو؟ طيب what happens next? As concentration increases here in the central compartment, هنا بصير بزيد. فببدأ إيش؟ The rate of elimination will start to increase. هذا constant ها. This is constant. This is constant. So this starts to increase. فبصير في الريت for elimination بيزداد until this rate of elimination is equal to the rate of input. فبصير عندنا الانبوت equal to output, وبهاي الحالة بصير عندنا ايش؟ التشينج هن شو بده يصير التشينج؟ zero. And this is when we reach what we call steady state concentration اللي هو CPSS. لما نوصل للسي بي اس اس خلص steady state. steady state معناته constant concentration. وبصير عندنا this equals this, يعني whatever gets in gets out. فبضل عندنا the concentration is the same, and we call it steady state concentration. Okay, let's now go to what is written here. See, this is your infusion rate given as K0. 0 here to note that you have zero order process. And this is your one compartment. And here is the window through which the drug gets out. Okay? You don't get confused by this one. Okay, just to say here that the drug is eliminated. If you remember, we said that V of dCp divided by dt had a differential equation. طبعا here we are talking about amount per time equal to the rate of input اللي هو positive واللي هو برضه amount per time ناقص اللي هو this is negative because it's removing the drug اللي هو rate of output اللي هو amount per time برضه V of KL في concentration. طيب, now you need to recognize now the integrated equation. This is your integrated equation during IV infusion. يعني خلال عملية الانفيوجن, not after stopping the infusion. إذن during the infusion. طيب, شوفوا شو بيحكي لكم. CP, which is the concentration at any time, صح؟ هذا متحرك. Okay, this is variable. And the time is this one. This is what we are talking about. And this is also variable. Then we have concentration and we have time. طيب, so CP equal to, شوفوا, K0 divided by V of KL اللي هو الكليرنس. شايفين؟ إذن K0 الانبوت divided by the clearance اللي هو V of KL multiplied F1 minus E to the power of minus KL في T. شوفوا, before قبل هيك في ال IV bolus administration we talked about E to the power of minus KL في T. Now we are talking about 1 minus E to the power of minus KL في T. Previously we called this إيش? Fraction remaining. Remaining. Okay? And it ranges from 0 to 1. What about this? طيب, this we call it accumulation fraction. Accumulation fraction. And it also ranges from 0 to 1. شايفين؟ طيب, لاحظوا التالي. at time 0 لما يكون الوقت 0, okay, E to the power of minus KL في T, هذا E to the power of 0 شو راح يكون؟ لأنه T 0 وبصير E to the power of 0 بيطلع لنا 1. 1 minus 1 0. 0 multiplied into this constant اللي هو K0 على V of KL. Everyone is constant. If I multiply 0 into anything, I will get 0. And this is the right thing. يعني at time 0, the concentration in the plasma will be 0. حلو؟ طيب, إذن 1 minus 1 0. Okay, هي 0. This is 0. Okay, accumulation fraction ما راح يكون في شيء accumulated في الجسم, صح؟ Nothing in our body accumulated, so 0. طيب, what happens after very, very, very long time? E to the power of minus very, very big number is 0. طيب, 1 minus 0 شو بتصير accumulation factor? 1 بيكون 1. يعني reached the 100% accumulation. وصل ايش ال 100% accumulation. بهاي الحالة السي بي بيكون وصل السي بي اس اس وبصير يساوي K0 على V of KL. And this is when you will get to your steady state concentration. إذن when are you getting to your steady state concentration? You will get to it after very, very, very long time. Okay? طيب, another way if looking into this يعني ايش نشوف السي بي اس اس حكينا when we reach CPSS DCP divided by DT مضروبة ب V هذا change will be zero صح and because we are at steady state and it's equal ايش هذا change zero and it's equal to K0 minus KEL في V في CP طيب now معناته ال K0 وال KL في V في CP they are equal عشان يصيروا zero so K0 will be equal to KEL في V في CP لاحظوا انه هنا CP I should have written CPSS لانه this only happens when we reach CPSS ف this is CPSS اذا CPSS equal to K0 divided by the clearance اللي هو V في KL okay اذا we learned two things now we learned how to calculate the drag at any time using this equation and how we can calculate the steady state concentration. طبعا please know the following that CPSS is our target يعني عادة when we want to design a dosage regimen I should know what I should target at يعني قديش بدي الكونسنتريشن so if you know your target اللي هو CPSS and you know the clearance of the drug in the patient what can you calculate you can calculate your infusion rate is that clear طبعا you will notice later that the problem here is with the time to reach a steady state concentration what is this time it's very long time let's look at the following okay what do you see here you see here time and concentration following IV infusion this is a normal graph paper see 0 10 20 30 0 10 20 30 and you will see that it's taking very long time to approach CPSS actually you will not reach it exactly and we learned about the CPSS and how to calculate CPSS so now let us solve the following example let's say a desired steady state plasma level of theophylline is let's suppose it's 15 milligram إذا لما أحكي لكم desired here I'm talking about my target إذا I'm talking about my CPSS that I need is 15 ايش milligram per liter I want you to know that why did they choose 15 this is depending on therapeutic window with therapeutic window for theophylline ranges from 10 to 20 معناته anything in between will be okay so they chose 15 okay كstart okay they have given you the half-life of the drug اللي هو 4 hours إذا أعطاني T half وإيش بقدر أجيب من التي half what can I get from the T half I can get ال KEL okay and the apparent volume of distribution معطيكم إياه ك 20 لتر إذا V equal to 20 لتر طب شو هو الانفيوجن ريت necessary يعني بده ال K0 طيب هنا this is the answer okay this is given اللي هي 15 K0 is required it's not given KL is you can get it from the 4 hours so you write KL equal to 0.693 divided by half-life اللي هو 4 hours ويساوي 0.693 divided by 4 hours and it's equal to 0.173 I believe خلينا نشوف Yes. طبعا what is the unit? Hour to the power of minus 1. ليش? Why hour? Because this is in hour. Okay. طيب. So what do I do? How do I get K0? If I multiply 15 milligram per liter, if I multiply it into KEL اللي هو 0.173 and then multiply it into V اللي هو 25 liters, I will get K0. Always check the units that they are in uniform with each other. So let me multiply KL في V في CPSS. طيب V is قديش حكينا ال V 25 liter. So 25 liter يساوي. طيب then I will multiply it into the desired concentration اللي هو 15 milligram per liter ضرب 15. See what this is the answer. So your answer is almost 64.968, almost 65. طبعا I can use the 65. طبعا الunit here milligram per hour. Why did I choose milligram per hour? شوفوا هاي بالمليجرام والhour شوفوا تاعت ال KL or تاعت ال half life it's in hour. Anyway طيب it was 64 point something. Suppose I make it 60. يعني you don't want to make it as 64.968. انتوا حبيتوا تكونوا cautious انه because theophylline is narrow therapeutic window drug. يعني الtoxic concentration is very close to effective concentration, so you decided to use instead 60 بدل 64. Let's say you wanted to use 60. طب if you use 60 what will happen? In this case if you use 60 شوف شو راح يصير في CPSS. Of course it will decrease because you are using a lesser infusion rate. So 60 divided by 0.17 multiplied 25, and this one will be your steady state in case you decided to use this infusion rate. إذا خلونا نشوف. An infusion rate of 60 milligram per hour will give us a CPSS of 14.1 milligram per liter, which is of course less than 15 milligram per liter. Is this a problem? It's not a real problem since it's very close to to the desired or target concentration. With 60 is more convenient compared to 64.9 something something. So this is more convenient. So I can use it actually provided I know the therapeutic window of this drug. اللي حكينا the therapeutic window from 10 to 20, which means 14.1 is good enough. Okay. طبعا we already talked that the time to reach steady state, الوقت عشان يوصل لsteady state is infinity. يعني if I go back to this figure, to reach from 0 to the steady state it takes infinity time. So many days, so many hours. طيب in order for us to understand how fast it gets to the steady state, let's calculate what we call accumulation T half. يعني if the steady state here is 25 نصه يعني 12.5 here. Okay. Now how long will it take to reach half the steady state? So we'll call it T half. This T half خلينا نفهم. I'm not talking here about elimination half-life, I'm talking about accumulation half-life. So to reach half this one, half the steady state اللي هو هذا CPSS, how long do I need? And I will call it accumulation T half. What we can do is the following. Remember your equation, Cp equal to infusion rate divided by clearance into 1 minus E us minus KL في T. This is your equation that you'll be working with. Okay? Now, remember that this is K0 KL في V is the CPSS. Okay? And I want to reach half the CPSS, so I will substitute this one by half CPSS or 0.5 CPSS, whatever. Okay, so now I can write the equation as the following. I will remove this. Okay, and also I will remove this. Okay, and I will use here T half is here T half. Okay, and here CPSS بدل K0 KL في V, and here I will use 0.5 CPSS. Of course this goes with this one, صح؟ بصير عندنا ايش؟ half is equal to 1 minus E us minus KL في T half. If I take minus E us minus KL في T half, I put it here, بتصير positive. And I take my 0.5, I put it here, بتصير negative. بصير عندنا E to the power of minus KL في T half is equal to what? Equal to 1 minus 0.5. طيب معناته 0.5. Okay, 0.5 will be equal to minus E us minus هذا sorry positive هاي E us minus KL في T half. طيب خلونا just to make it clear, E us minus KL في T half is equal to 0.5 صح؟ If I take ln both sides بصير minus KL في T half is equal to minus 0.693 إذا أخذت لن الطرفين. If I take ln both sides طبعا negative goes with negative وضل عندنا T half is equal to 0.693 على KL. What a surprise! شو السربرايز تاعكم؟ إنه the accumulation half-life is the same as the elimination half-life, which means to reach half the CPSS I need 1 T half. Okay, بوصل 50% 50% of the CPSS. طيب من 50 to 100 في عندنا 75% صح؟ يعني في النص in the middle is 70. I need another 1 T half. إذن I need 2 T halves to reach 75% of CPSS. طب عشان أوصل in order to reach 87.5 يعني half the way from 75 to 100, 87.5, I need another 1 T half. Exactly very similar but in opposite way to the elimination half-life. So look at the following. I need 2 half-lives to reach 75. I need 3 half-lives to reach 87.5%, 4 half-lives to reach 94, 5 half-lives to reach 96 point something. And I can assume that practically again to reach about 96%, almost the CPSS, I need 5 half-lives, or to reach 94% I need 4 half-lives. معناته انتبهوا, please pay attention. The time to reach steady state, مش to reach, خلينا نحكي approach نقرب يعني. Okay, the time to approach steady state depends on the elimination process or elimination half-life. Okay, معناته طيب if I have drug A drug B. Drug A has a half-life. أيوة بدنا نشوف. Has a half-life of 6 hours. Drug B has a half-life of 12 hours. Which one will reach the steady state faster؟ طبعا drug A. إذا لاحظوا إنه مش معتمد, doesn't depend on K0. It depends on the half-life of the drug. That's why drugs with shorter half-lives reach the steady state or approach the steady state much faster than drugs with longer half-lives. Okay? I hope this is very clear. In any way, we agreed that it takes a very long time to reach steady state or to approach steady state. For theophylline, if you remember, I said that the therapeutic window might be from 10 milligram per liter up to 20 milligram per liter. So if I give the infusion, I may start to expect to see some effect when I reach 10 milligram. طب how much this will take? يعني how long will it take to reach the 10 milligram? How long? Okay, I can do that. I can use this equation, اللي هي infusion equation, and see when I will reach 10 milligram. طبعا provided that I use 60 milligram per hour. طبعا in this case it will give me 14 CPSS تاعه 14.1, يعني بصير 10 equal 10 equal to CPSS اللي هو 14.1. من وين جبتها هاي؟ From the previous example. Okay, multiplied 1 minus e to the power of minus KL. KL I know my KL اللي هو 0.17 في t which I need to calculate. يعني what I need to calculate now is how much time, قديش وقت it will take to reach the minimum effective concentration اللي هو 10. I'm not talking about CPSS. I'm talking about the minimum concentration. Okay? Okay, watch here. K0 is 60, KL is 0.17, volume distribution is 25, CP required is 10. So they used, substituted the numbers as I told you, and in the end they got that 0.708 equal to 1 minus e to the power of minus 0.17 t. طبعا you can take this one there and this one here and then take ln both sides. المهم في النهاية t is gonna be 7.24 hour. يعني what I mean to tell you is, imagine that we need 7.24 hours just to reach the minimum effective concentration. يعني the patient might die before the drug starts to give an effect. What does this tell you? Does it tell you that an infusion is bad? Let's give it by oral? No, it tells you that we can have other ways to reach the steady state faster. And this is what we'll be talking about inshallah in part 2. هنا it will show you how, or the time to reach steady state, which depends on the half-lives. So we get to this number after 1 half-life, 2 half-lives we get here, 3 half-lives we get here, and so on. So we need at least 4 or 5 half-lives to get very close to the CPSS. I hope you enjoyed this topic. It's simple, very simplified. If you have any question, please do not hesitate to ask me. Thank you.